In the previous video, we introduced a type of energy that we called enthalpy, delta H. And we said that enthalpy was the amount of energy that's either given off or taken in by a reaction due to the difference in energy between the reactants and the products, and that energy difference can be experienced in the form of heat. Now, there's another type of energy we want to introduce here, and it kind of sounds similar to enthalpy, so we have to be careful. But it's called entropy. Okay, and entropy, well, there's some pretty complicated descriptions of what entropy is, but for us, we can simplify things down a little bit and say that entropy is simply the measure of disorder. Okay, and the laws of thermodynamics tell us that the entropy of the universe is always increasing. And there's no way around that. Okay, so generally speaking, we can say that if entropy is constantly increasing in the universe, then we can say that the disorder of the universe is always increasing. And I think this is something that we can witness in our own observations. For example, you can imagine if you were to not take care of your lawn for several years, the amount of disorder would definitely increase during that time. Also, if you were to imagine taking a glass and dropping it on the floor and watching it explode into all these little shards of glass, okay, going from having a glass that's completely intact to a glass that is completely broken down into tiny parts scattered all over the place in random fashion, that is an increase in entropy. Notice that we don't routinely see shards of glass spontaneously kind of going back together and reforming what they started off as. Okay, that would go against entropy. Now, that's not to say that entropy has to always increase within a system. It just has to constantly increase in the universe. So in principle, I could take those shards of glass and glue them back together again. And if I did that, I would be working against entropy, but I would have to put work into that. Okay, so there's a way of getting around it if you need to. And what's interesting is that you'll find that the work that you do to fight against entropy by itself will actually increase the entropy of the universe. And I know it's kind of a tricky thing to wrap your brain around. Now, entropy is symbolized by the letter S. And for any process, we can have a change in entropy, which we call our delta S. Okay, so in the case of the glass being dropped from the counter onto the floor and breaking up into thousands upon thousands of little pieces, the change of entropy is positive. It's increasing. Okay, we've gone from being more ordered to being more disordered. Okay, the other way around, though, is not something that we typically observe. Okay, here we're going from being disordered to being more ordered. And in that case, our entropy is going to be a negative value. Now, how does this relate to chemistry? I mean, we don't talk much about breaking glasses in chemistry, although in the laboratory it does happen. But we could have a chemical reaction that shows an increase in energy. For example, if you were to imagine going from water in the liquid phase and add heat to that so that it converts over to the gas phase. Okay, we're going from water molecules that are fairly close to one another, moving relatively slowly, to water particles that are fairly spaced out and really moving around fast and bouncing off the containers. If I was trying to keep track of one of these things, it would just be impossible. Okay, so this process of going from a liquid to a gas shows an increase in entropy. Okay? In fact, many of the properties of chemical reactions that lead to an increase in entropy also lead to an increase in the amount of gas. Another example of entropy at work would be in the reaction of, let's see here, taking a solid like sodium chloride and adding water to it so that it becomes solvated. Okay, where each individual ion is completely surrounded by water molecules. But think about what sodium chloride looked like before adding water to it. We had the ions all lined up in a very regular repeating pattern. Whereas afterwards, these ions are being separated from one another. Okay, and they have water in between them. Okay. Not only that, we went from having just NaCl to having an Na and a Cl. We have two more particles. Okay, so overall, what we can say is happening here is an increase in entropy. Okay, another place where we see an increase in entropy is going to be a reaction where we have more particles or more molecules being produced than what we started off with. For example, we could take liquid water and we could electrolyze this to form hydrogen gas plus oxygen gas. Okay, if I balance this out, what you see is we go from 3 particles, I'm sorry, I can count. We go from having 2 particles on one side to having 3 particles on the other side. Okay, and that gives more randomness, that gives more positions that the particles can find themselves. And again, this is going to increase the entropy. And of course, going in the opposite direction for any one of these, going from here to here, or here, or here, is going to cause a decrease in entropy. Okay, so with this we can make some generalizations. Okay, for a reaction or any process to be spontaneous, okay, we want it to be enthalpically favorable. In other words, so if we want something to be spontaneous, okay, the delta H should be negative. Okay, because a negative delta H means that we're going from high energy to low energy. And that's kind of the natural state of things, or natural order of things. You can ski downhill, but it's rather difficult to ski uphill. Okay, and we need the entropy to be increasing. So an increase in disorder. For a process to be non-spontaneous, okay, the enthalpy would be positive, so going uphill in energy, and we would be getting more ordered, so the entropy would be negative. Okay, but what happens if we get some other situation where we have a delta H that is negative, so that's definitely going to favor us being spontaneous, but we have a delta S that's also negative, which tells us it should be non-spontaneous. Well, it depends upon which one of these two factors is larger, and that allows us to actually calculate whether or not a process is going to be spontaneous. Now, we're not going to get into this too deeply, except to say that there's another type of energy that we call the free energy, okay, which we symbolize as delta G. And the free energy is a measure of the amount of energy available for a system to do work. Okay, and the delta G actually depends on both the entropy and the enthalpy. And again, this is as far as we're going to get into this. Okay, but this equation shows us that this overall deciding factor, this presence of free energy, is going to be determined by delta H and delta S. Okay, and we can make the generalization that if our delta G is equal to a negative value, then the reaction is spontaneous. It'll happen. Whereas if delta G is a positive value, it won't be spontaneous. Okay, and that's the relationship that we need to be familiar with here. Okay, so if we take these three different types of energy here, we have delta H, delta S, and delta G. Okay, delta H tells us if we're going uphill or downhill in energy. Okay, delta S tells us whether or not we are following the natural order of nature, which is for disorder to be increasing. And then the delta G kind of takes both of those factors into account to determine overall whether or not a reaction will be spontaneous. Now, when we've talked about the energy of a reaction previously, we said that we can describe the course of the reaction in terms of the relative energies of the reactants and the products. So if we were to draw a energy profile for this particular reaction, where we look at the reaction progress and the energy for each one of the components. And let's say for this reaction, we'll have it be exothermic, which means the products are going to be lower in energy than the reactants. Now, in the past, we kind of looked at this as a big energy jump where we saw that heat could be released here, as this was an exothermic reaction. But you have to think about this. If I can put chemical A into a flask, that means it must be somewhat stable. So what is its reason? What's its motivation for going on to react to produce B? And usually that motivation comes in the form of energy. So the path that I've shown going directly from A to B is not what really happens, but rather we see energy getting pumped into the system until we reach kind of a breaking point. Okay, and that breaking point is what we call the activated complex. You may also see this referred to as the transition state. Okay, and that high point in energy right there then quickly drops off and takes us to our products. All right, just about every single reaction is going to require that some energy be put into it in order for the reaction to proceed. If you consider something like the combustion reaction, if you take methane or any hydrocarbon and you combust it, it's going to release heat. We see that anytime we look at propane being burned or methane being burned. But in order to get that reaction to get started, you have to provide the spark, okay? And that spark is that amount of energy needed to kick things off. Okay, that energy is measured from the energy of the activated complex down to the energy of the reactants. Okay, and we call this the activation energy. Okay, and the higher the activation energy is for a reaction, the slower it's going to proceed. Okay, so if activation energy is large, that means it's going to take a while to get enough energy in there for the reaction to proceed. Okay, so that means the reaction will be slow. Okay, and the activation energy is small. That means that the reaction will be faster. Okay, so if I'm looking at two different reactions, so let's say A going to B and C going to D. Okay, and I will draw two energy diagrams here. Okay, and we'll say that both of these reactions are exothermic. So in both cases, the products are lower in energy than the reactants. Okay, now let's say that the reaction on the left follows a path like this, whereas the reaction on the right follows a path like this. Okay, now we're going to assume that the two reactions are on the same scale. In other words, we'll call this 0 and this, we'll call it 100 kilojoules or whatever you want to have. Okay, just to show that this is on the same scale. Okay, the activation energy for the reaction on the left is represented by this distance here. The activation energy for the reaction on the right is represented by this distance. Okay, so as we can see here, there's an activation energy for each reaction. Okay, but clearly the reaction going from C to D has a much higher activation energy. So the activation energy is much, much, much greater for the reaction on the right than than for the reaction on the left. Okay, and for this reason, we can deduce that A being converted to B is faster than C being converted to D. Okay, now, when we talk about how fast a reaction is going, what we're talking about is the rate of the reaction. Okay. Now, when we say the rate of reaction, it's kind of like talking about the speed of a car. Whereas with a car, you talk about the distance traveled over a period of time. With reactions, we're talking about the change in the concentrations of either the reactants or the products. So if I have some reaction of A plus B giving C, okay, I can describe the rate as being equal to the change in the concentration of C divided by the change in time. Okay, but I can also put it in terms of the reactants as well, but we're not going to worry about that. I just want you to kind of wrap your brain around this concept that the rate of a reaction, okay, can be described in terms of changing concentrations over time. So you can imagine that if we were to track how much C was present, and we have the ability to do that, okay, over the course of time, that we would start off with a very low concentration of C because it's the product. It hasn't formed yet. Okay, but then over time, the concentration would increase and then eventually level off when we got to the end of the reaction. Okay? And again, some reactions are going to be faster than others. Okay? Some reactions are going to have a faster rate because they have a lower activation energy. Now, what governs the rate of a reaction is going to be what's called the rate law. Okay, and the rate law for a reaction relates the rate of the reaction to the concentration of the reactants. So rate is equal to this constant, which we'll call K, times the concentration of one of the reactants raised to some power, which we'll call X. Okay, so for example, we could have a reaction that has a rate that is equal to the rate constant times one reactant raised to the second power times the second reactant raised to the first power. Okay, I don't want you to get too caught up in this because we're not going to try to calculate these ourselves. But what I want you to focus on here are these numbers. Well, the one that's imagined to be here. Okay, we can say that the reaction is second order in A, whatever A happens to be. Okay, it's first order in B. And then we can add these together and say that it's third order overall. Now again, I don't want you to try to derive a rate law. I just want you to be able to look at a rate law and be able to identify what order it is in each reactant and overall. Now, the reactions that we've looked at so far have been reactions that kind of just go in one direction. In other words, A can only go to B. But there are some reactions where the backwards process is also possible. In other words, once you get to forming some products, you wind up having the products convert back to the reactants. And the way that we express this is through a special type of arrow that points in both directions. Okay, and we call this process equilibrium. Okay, equilibrium kind of has this kind of sounds like it's about balance, and it is about balance, but it's not always an equal balance. So let me give you an example here. Let's keep on working with this hypothetical reaction A being converted to B. Now, at the very beginning of the reaction, okay, we're not going to have any B laying around. Okay, so initially, the concentration of B is going to be 0. And let's say the concentration of A is just some number, it could be 1 or whatever. Now, think about what's going to happen. As the reaction proceeds, the concentration of A is going to start dropping off. At the same time, the concentration of B is going to start increasing. Okay? And this is going to continue on until eventually we get to the point where the rate of the forward reaction equals the rate of the backward reaction. And after a period of time has passed, we find that the concentrations stop changing. Okay, this region where things have kind of leveled off here is the point where we have reached equilibrium. Okay, what I don't want you to do is to think that somehow the reactions have this, or the molecules within the reactions have some sort of internal clock that tells them, okay, well, once we get to a certain point in the reaction, we're going to stop reacting, because that's not what happens at all. In fact, in this region that I have shaded and called equilibrium, the reaction's still going back and forth. Okay, between the reactants and the products. It's just that it's happening, or both processes are happening at equal rates, so we don't see a difference in concentration. Okay, but so that's what equilibrium is. We've gotten to a point where the reaction doesn't go forward anymore and it doesn't seem to go backward anymore. Okay. Now, like I said, things haven't come to a standstill, but we do have this perceived stability in the concentrations. But there are some things that can affect equilibrium. We refer to what's called Le Chatelier's principle. And essentially what Le Chatelier's principle tells us is that a system at equilibrium, when stressed, will shift. I'm sorry, not shift, will respond in a way that alleviates the stress. Okay, so there's a couple of different ways that we can stress a system. And the biggest way we can do that is through concentration. Okay, if I have a reaction where A is being converted to B, and this is an equilibrium process, okay, and let's say that we have achieved equilibrium. If I were to add more of A, so increase the concentration of A, what this does is this causes the equilibrium to shift to the right. Okay, so we'll make more B. So the equilibrium will shift towards more product. Okay, when we say more product, we usually refer to it as shifting to the right. Okay. if I were to increase the concentration of B, then we would see a shift in the opposite direction, a shift to the left. Okay, so when we increase the concentration of A, okay, we have too much A, not enough B. So what happens is the reaction takes that A and converts it over to B. Okay, so that's how we get that shift to the right. If I add more B, okay, the reaction is going to shift the B over to A. So that's why it's shifting to the left. We can also affect this by decreasing concentrations. And there's ways of doing this. But if I were to decrease the concentration of A, I wouldn't have enough A anymore. So B would be converted to more A. So again, a shift to the left. And if I were to decrease the concentration of B, then there wouldn't be enough B and there'd be too much A. So the reaction takes some A and converts it over to B. Therefore, a shift to the right.